Again, welcome to Inferential Statistics in Decision Making. These lectures cover the basic concept of probability. So our main objective is to identify the sample space of a probability experiment, also use the fundamental counting principles. We're also going to distinguish among classical probability, empirical probability, and subjective probability. We're also going to determine the probability of the complement of an event and also use a tree diagram and the fundamental counting principles to find probabilities. So first, we start with the probability experiment. It's an action or a trial through which specific results, such as counts, measurements, or responses are obtained. An outcome is the result of a single trial in a probability experiment. A sample space will be all the possible set of outcome of a probability experiment. Again, we're going to see an example soon. And an event will consist of either one or more outcome, and it will be the subset of the sample space, because again, the sample space is the set of all possible outcome. So an example for a probability experiment will be to roll a die or toss a coin. Now, if I roll a die, the outcome can be 1, 2, 3, 4, 5, 6, because a die has 6 sides. Now, if I toss a coin, the outcome will be either the head or the tail. It's to be only one at a time, either the head or the tail. Now, the sample space for rolling a die will be all the possible outcome, which will be from 1 to 6. And the sample space for tossing a coin will be head and tail. It's only 2 possible. Now, an event can consist of one or more outcomes. So in terms of tossing a coin, one event can be head, another event can be tail, or if we toss it twice, we can get 2 head or 1 tail and 1 head. So let's see the example here also. Here, the probability experiment, here we are rolling a die. Outcome can be 3. Sample space will be all the possible outcomes, so from 1 to 6. Event can be any event where we have only one outcome or more than one. So a die is even, the possible is 3, 2, 4, 6. Now, next example is to identify the sample space. Here we have a probability experiment, consists of tossing a coin and then roll a 6-sided die. Describe the sample space. Now here is combination of both tossing a coin and also rolling a die. We know if we toss a coin, the possible outcome, head and tail. When we roll a die, the possible outcome will be from 1 to 6. So here we say there are 2 possible outcomes when tossing a coin. Either we have the head or the tail. Now for each of these, there are 6 possible outcomes when you roll a die from 1 to 6. So one way to list the outcome for actions occurring in the sequence is to use a tree diagram. So this is again our possible outcome. Again, the tossing a coin is only 2 options. So either we have head or the tail. So let's assume we start with the head. Now, when we get a head, there's a possibility that we can get head and 1. When we roll the die, we can get either 1, 2, 3, 4, 5, 6. So we have a possibility of H1, H2, up to H6. The same thing if the coin is a tail, then we also have a possible of 6 outcomes from 1 to 6 for rolling the die. So we get from T1 to T6. So this means the sample space, which will be all the possible outcome when I toss 1 coin and also I roll 1 die, is 12 outcomes from H1 to H6 and also from T1 to T6. Next is the simple event. We say the simple event is an event that consists of a single outcome. So for example, tossing heads and rolling a 3. So this is H3. This would be a simple event, one event. So again, a simple event is an event that consists of a single outcome. Now, an event that consists of more than one outcome is not a simple event. So example here, tossing the heads and rolling an even number. So we have possible 3 even numbers. So H2, H4, H6. So this is not a simple event. Again, a simple event means we have only single outcome. A good example is H3. I toss the coin, I have head, they die together, and only possible one outcome at a time, I have 3. So here they say we should identify a simple event. Determine whether the event is simple or not. You roll a 6-sided die, and event B is rolling at least a 4. Again, you roll a 6-sided die, and event B is rolling at least a 4. So this is not simple. The reason why we say at least a 4. So event B has 3 outcomes, 4, 5, 6. Because we said event B is rolling at least a 4. So that will be 6-sided, so we have 4, 5, 6. So it's not a simple event. Now, next is the fundamental counting principles. Here we say that if one event can occur in m ways, and also a second event can occur in n ways, the number of ways the 2 events can occur in sequence will be m times n. And this is again used a lot in many mathematics concepts. So this can be extended for any number of events occurring in sequence. Now we have a question here saying you are purchasing a new car. The possible manufacturers, the car sizes, and the colors are listed below. So we have 3 manufacturers, which is Ford, GM, and Honda. Then the car size can be either compact or mid-size. The color can be white, red, black, and green. Now, how many different ways can you select one manufacturer, one car size, and one color? Use a tree diagram to check your results. Now, the possible way would be the manufacturers are 2. So it will be 2 times, the car size is also 2. So 2 times 2, the colors are 4. So it times 4. So the answer will be 2 times 2 times 4, which will give us 16. Now let's use 3 times. Let's go back. The manufacturers are 3. Okay, I said 2. So we have Ford, GM, and Honda. So it will be 3 times 2 times 4. So that will give us 24. So we have 3 manufacturers. So 3 different type of, the size car is only 2. And the possible different colors are 4. So it will be 24 ways. Now we can come up with a tree diagram. First, let's start with the number of manufacturers. So we have Ford, GM, Honda. Now we know the number of size is only 2. So the possible Ford we can have either compact or mid-size. Same thing apply to GM, compact or mid-size. Honda also compact or mid-size. Then all these 3 different car models or manufacturers, we have possible, again, 4 colors. So this means compact have 4 different colors, mid-size 4 different colors for Ford. The compact has 4 different colors, mid-size 4 different colors for GM. Same thing applies to Honda. The compact is 4 different colors, mid-size. So when we count all the last section here, we should get 24. So we can see we have 4 plus 4 is 8, plus another 4, 12, 16, 20, and 24. So it's the same as 24. Now let's go to the different types of probabilities. As we said earlier, we have 3 different types of probabilities. We start with the classical probabilities, which is more common. And also we have the empirical probability, and also we have the subjective probability. So classical or theoretical probability, each outcome in a sample space is equally likely. So rolling a die or tossing a coin is a classical probability. Based on the definition, each outcome in a sample space is equally likely. So when I roll a die from side 1 to 6, they all have equal chance of being selected. Or to toss a coin, the head and tail, they all have equal chance of getting one of them. So that's why here we say that the probability of an event, E, is the number of outcome in event E divided by the number of outcome in sample space. So for example, what is the probability of rolling a die? We will get even number. We know out of the 6 side, 3 of them are even. So it will be 3 divided by 6. 6 is the sample space. The number of outcome is 3 even numbers. So that's example here. Here they say we should roll a 6-sided die. We should find the probability of each event. Event 1 is rolling a 3. So we have only 1, 3. Then all the sample space will be 6. So the answer will be 1/6. The probability of rolling a 3 will be 1/6. Event B, the probability of rolling a 7. Again, we don't have no 7. So that will be 0. Because we know, again, a die have only 6-sided. So the answer will be 0. For example, what's the probability of rolling 10? We don't have no 10, so the answer will be 0. Next, event C, roll a number less than 5. Now, to roll a number less than 5 means we have 1, 2, 3, 4. So the probability of rolling a number less than 5 will be 4 divided by 6, because we have 4 numbers that are less than 5. And the total outcome or the sample space is 6. So it will be 4/6. Next, let's look at the empirical probability, which we also call the statistical probability. Now, this is based on observation obtained from probability experiments. So that's why it's called empirical. This means an event occurs before. Based on that result, we can predict what we are going to get now. So that's why it's a statistical probability. Because in statistics, for example, inferential statistics, that's our main goal. So here, it still have a relative frequency of an event because this event has occurred before. So the probability of E is the frequency of event E divided by the total frequency. So let's see this example. A company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. So far, 320 people have responded to the survey. What is the probability that the next person that responds to the survey says that traffic congestion is a serious problem in their community? Now, this is not a classical problem because we are going to get our result based on what previous respondents gave us, the survey result. So we already have a survey of 320 people. We know the result already. So based on that result, we can predict or say what the next surveyor may say or the next person may say. So here the question is, what's the probability that the next person that responds to the survey says that traffic congestion is a serious problem in their community? So this is our result here that we know already. Out of the 320, the serious problem is 123, a moderate problem is 115, not a problem is 82. Our question said, what is the probability that the next person that responds to the survey says that the traffic congestion is a serious problem? So it will be 123 divided by 320. because 123 said it's a serious problem. So now we can see the difference between classical probability questions like rolling a die, tossing a coin, we saw, and also empirical probability based on previous results or events. So here again, we say the serious problem is 123. So the probability that a next person may say the traffic or the problem is a serious problem, it will be 123 divided by 320, which will give us 0.384. Next, we talk about the law of large numbers. Now, the law of large numbers states that it's an experiment. When an experiment is repeated over and over, the empirical probability of an event approaches the theoretical, which is the actual probability of the event. So example given here, let's say we have an experiment we are doing. Now, when we toss a coin, maybe 2 times, 3 times, the answer may vary. Let's say 50 times, we may still see vary. But after we toss for so many times, it will remain constant. In this case, tossing a coin, we have 2 sides. So we may have 50% on each side. And this even gives us the idea of in statistics, when the sample size increases, the results get closer to the population. We may talk about this when we start differential statistics. For example, if I use a very small sample size to make an experiment, most likely the result will be different from if I use the whole population. But if the sample size is close to the population, or is the same as the population, then our result will be the same as the population. So our last types of probability is what we call the subjective probability. Now, subjective probability, there's not too much mathematics here. The whole thing is based on your intuition, educated guesses, and also estimates. You can estimate. For example, let's say Yankee baseball team has won the baseball World Series. Out of 20 years ago, they have won it 10 times. Well, I can't use empirical probability that, okay, out of 20, they won 10. So this year, they have 50% chance of winning. No, we cannot. That's empirical probability. The problem here is that in a baseball team, there are so many factors. Maybe Yankees team have a good coach, or they have a very good player that changes the whole game, or maybe other factors. So we have to consider the conditions. So that's where we have to make an educated guess or our intuition based on the team performance. So example they gave us here, doctor may feel a patient has 90% chance of full recovery. This is not based on anything, maybe based on the doctor's educated guess or estimate or intuition. So next, let's classify the statement as an example of classical, empirical, or subjective probability. The first is the probability that you'll be married by the age 30 is 0.50. Well, depends. But based on this question, we may say that this is a subjective probability. Most likely an educated guess. The next, the probability that a voter chosen at random will vote Republican is 0.45. This can be again empirical because it can be based on previous voting that he has done. So again, the probability that a voter chosen at random will vote Republican is 0.45. So most likely based on a survey, empirical probability. The probability of winning 1,000 ticket raffle with 1 ticket is 1/1,000. So this would be classical probability. classic, equally likely outcome. Now we start with the probability rules. So range of probability rules. First, the range of probability rules, we always say that probability values always will be between 0 to 1. When we say a probability of an event is 0, that means it will never happen. And when we say the probability of an event is 1, that means we are 100% certain that it will happen. Now, between 0 to 1, it can be 0.5, 0.3, etc. So here we say probability of an event, E, can be greater than or equal to 0, but must be less than or equal to 1. Now, the next rule is the complementary event. The complementary of an event means if the event is normally in computer science, we may say if something is true, the complement of true means is false, or complement of 0 is 1. And the whole concept also is the same here. So the complement of E means it's not E. So the Venn diagram will tell us everything that is in E, the complement of it is not in E, to be outside. So here we say the set of all outcomes in a sample space that are not included in the event E. So normally to find, if we know the event E, to find the not E, we will say the universal or all the possible probability, let's say 1 minus whatever the event E is, probability of event E. So let's say probability of event E is 0.6, then probability of the complement E will be again 0.4. So the total will be 1. So probability of complement E plus probability of E will be 1, because probability of E is equal to 1 minus probability of complement E. Or probability of complement E also is the same, 1 minus probability of E. Now, let's see example here. Here they say you survey a sample of 1,000 employees at a company and record the age of each. Find the probability of randomly choosing an employee who is not between 25 and 34 years old. Now, this is our data here. We have employee ages between 15 to 24. We have 54 of them. Between 25 to 34, we have 366. Between 35 to 44, we have 233. All the way to 65 and over is 42. And the total employees is 1,000. Now, the question says we should find the probability of randomly choosing an employee who is not between 25 and 34. So if it's not between 25 and 34, we have to remove the 366. So we are going to add all the remaining values and we divide, or I would say that it will be 1,000 minus 366 divided by 1,000. Now, for example, what's the probability that the employee will be 65 years or over? Then it will be 42 divided by 1,000. What is the probability that the employee will be 45 years and over? It will be 180 plus 125 plus 42 divided by 1,000. So let's see the solution here. As we said earlier, the probability that the age is between 25 to 34, we say 25 to 34 is this. So it will be 366 divided by 1,000. Now, probability that the age is not that amount, then we're going to subtract 0.366 from 1, and that will give us 0.634. So I'm looking for probability that it's not 25 to 34. Okay, so I can find the probability of is 25 to 34. The answer I get, I will subtract it from 1. Or another option here is that I'm going to add all the values. So all the employees are 1,000. So I'll say 1,000 minus 0.366 divided by 1,000, and that should give you 0.634 also. Another example here, probability experiment consists of tossing a coin and spinning the spinner shown below. The spinner is equally likely to land on each number. Use the tree diagram to find the probability of tossing a coin and also spinning an odd number. So first we start with our tree diagram. We have the tossing a coin, we have only a head and a tail. And also the spinning, as we can see, has 8 sides from 1 to 8. So combination, possible tree diagram, we are going to get from H1 to H8, T1 to T8. So the possible will give us 16. Because tossing the coin, we only have 2 outcomes. Then within any of the 2 outcomes, for the spin is 8 sides. So we have 8 for head, 8 for tail. Now the question said, use the tree diagram to find the probability of tossing a tail and spinning an odd number. So what we need here is a tail, which is T, and we need only the odd numbers. So it will be T1, T3, T5, and T7. So that's our main goal. So we count how many possible is 4. 1, T1, T3, T5, T7. So we have 4 of them. And the total outcome again is 16. 8 for head, 8 for tail. So we get 4 divided by 16. That gives us 1/4, and that will give us 0.25. Let's try another example here. Your college identification number consists of 8 digits. Each digit can be 0 through 9. And also each digit can be repeated. What is the probability of getting your college identification number when you randomly generate 8 digits? Now, here we say that each digit can be from 0 through 9. And we want to generate 8. And also, we can repeat each digit. So let's see here, each digit can be repeated, and we have 10 choices for each of the 8 digits, because from 0 to 9, again, is 10. So we use the fundamental counting principles, and there are 1, 2, 3, 4, 5, 6, 7, 8, because in each digit, we have possible of 0 to 9 to select. So we have 10. Second digit, the same thing, 0 to 9, because we can repeat. Now, if we cannot repeat, then it will be 10, 9, 8, 7. And anytime we take one digit, we are going to reduce it by 1. But since the question said we can repeat it, we just have 10 options for all the 8 digits. So this will give us 10 to the power 8, or we say 100 million possible identification numbers. So that is the total outcome, or the sample space. Now, only one of those numbers correspond to your ID number. So now the probability of your ID number will be, again, 1/100 million. Again, if we don't need to repeat the digit, then the first digit, the possible outcome is 10. By the second digit, the possible outcome will be 9. Then we have 8, 7, etc. So we are going to end the lectures here. So in these lectures, again, we learn the basic concept of probability, especially the definitions. For example, what is a event, sample space, etc. And also we learn 3 different types of probability, which is, again, classical probability, subjective probability, and also empirical probability. So again, see you in the next class. Thank you.